In Chapter 11, we talked about electrophilic additions, mostly in the form of a Bronsted acid being an electrophile that adds to pi electrons. We started to generalize a little when we realized that carbocations can be electrophiles as well, leading to polymerizations and other really cool reactions, like the formation of terpenoids. In Chapter 12, we will deal with electrophiles that have extra electrons. When these react, they can actually form a ring with the alkene carbons, which allows all the atoms to maintain an octet. There is still some destabilizing charge in many cases, but the intermediate is much more stable than a carbocation on its own. While these reactions are similar to those discussed in Chapter 11, we'll have much more stereochemistry to consider. At the first step, we already form two enantiomers of the same intermediate, depending on the direction from which the electrophile adds. In some cases where the molecule has a high degree of symmetry, this may not matter, but in many cases it will lead us to mixed products. We will discuss many examples of an electrophile that also has a lone pair, which we abbreviate as an E colon. The first of these is a carbene. Carbenes are somewhat bizarre. They have only two bonds and one lone pair, which makes them uncharged but still electron deficient. The carbene is very electron deficient, similar to the carbocation, and can serve as an electrophile. However, if this reacts as an electrophile, we now have a negatively charged carbon which is highly nucleophilic. Carbenes are therefore highly reactive, and we can only generate them in solution. One source of carbenes we've already seen in Chapter 10. Diazomethane, CH2N2, in that example picked up an acidic proton with the lone pair and quickly went through an SN2 mechanism to release nitrogen gas. In this case, the nitrogen gas can be released from diazomethane directly by the addition of heat or light. The highly reactive carbene then can go through an electrophilic addition, forming two carbon-carbon bonds simultaneously and leading to a cyclopropane product. Cyclopropanes are high energy, but so are carbenes, and this reaction can be pushed readily to the cyclopropane. Carbenes can also be generated as dichlorocarbenes in solution by hydroxide in the presence of chloroform. Those are the reaction conditions shown. The three chlorines make the chloroform hydrogen more acidic by the inductive effect. The molecule is charged, and that charge can be released by the heterolysis of chlorine. This is slow, but the presence of the chlorines allow for resonance structures that can fill the carbon octet, making the carbene a little bit more stable. The carbene, like before, can form a cyclopropane derivative, only this time with two chlorines on the added carbon. Halogens can also function as electrophiles, which we saw in our alpha halogenation reactions in Chapter 10. Because a halogen has extra electrons, they are examples of E colon. But in this example, the ring that is formed is not the product but an intermediate, and the other bromine has to add to make the final product. When we form the final product in this example, both trans products are formed, but in a racemic mixture of the two trans enantiomers. Let's think about how this works. Molecular bromine can have an induced dipole due to its polarizability. The positively charged bromine serves as an electrophile, while the negatively charged bromine serves as a leaving group. The extra lone pair on bromine can ensure that both carbons have complete octets. The resulting ring is called a bromonium intermediate because of its positively charged bromine. This is an exceptionally good leaving group, and the bromide ion can serve as a nucleophile for an SN2 reaction from the other side of the carbon-bromine bond. Notice that bromine could have just as easily attacked the other carbon-bromine bond, and we'd ended up with the other trans isomer. This is a reaction pattern that we also observe for chlorine. We again get anti-addition of Cl2, indicating a chloronium intermediate analogous to the bromonium intermediate. Just like when we added haloacids to alkynes in one equivalent, when we add molecular halogens to alkynes, we end up with both syn and anti-additions to make a mixture of products, and yields aren't great. If we instead add excess molecular halogen, we end up with a complete conversion to the tetrahalide in actually pretty good yields. Because water can't add to an alkene without an acid catalyst, molecular halogens are free to react with alkenes even in aqueous solution. However, Now the most concentrated nucleophile in the reaction is water, and we end up with an anti-addition of the halide and hydroxy group. We call these reaction products halohydrates. These molecules are precursors to epoxides, which we saw before. Halohydrogen formation can be somewhat regioselective, much more readily adding the OH group to the more substituted carbon. This is very similar to the reaction of epoxides in acidic conditions. The bromonium, because it is positively charged, will already have a weaker bond between the more substituted carbon and the bromine. Water will come in and react at that position more readily, which means we'll have more product with the OH on the more substituted carbon. Halides are relatively rarely included in biological structures, but when they are, it's often in the product of electrophilic additions. Some of the more common natural examples come from marine algae. This is particularly interesting when you think about the fact that you are unlikely to have molecular halogens like Br2 occurring biologically. Aqueous halide anions are actually used to generate bromoniums from bromides, which requires oxidation, and is also pretty cool. We already talked about being able to hydrate alkenes with water in the presence of dilute acid. This is often a very desired reaction. Alcohols can go through all sorts of reactions. However, this reaction proceeds through a carbocation and can rearrange. Notice that the alcohol doesn't add to a carbon that was part of the original alkene, as shown here, because the carbocation intermediate was rearranged. To avoid this, we can go through a two-step process called oxymercuration reduction, which is an electrophilic addition reaction followed by a reduction. It will give the product with no rearrangement. The trick here is the mercury 2 acetate. Mercury is positively charged and therefore electrophilic, but still has a bunch of d electrons that can easily help to form a cyclic intermediate with complete octets, as shown. Due to this cyclic intermediate, the water will add anti to the mercury, and since the mercuric intermediate was positively charged, the water will add to the more substituted side following the Markovnikov rule. After this reaction, the water is fixed in place. Sodium borohydride is able to reduce the mercury and replace the carbon-mercury bond with a carbon-hydrogen bond, but the reaction racemates the less substituted carbon. In this case, it doesn't matter because that carbon doesn't happen to be chiral anyway. Here's a case where it does matter. This reaction adds the alcohol without any selection towards one enantiomer or the other. When the mercury is reduced off, the product is produced with a slight preference towards anti-addition of the hydrogen, but generally very little regard for stereochemistry. Mercury salts can help us to react water with alkynes as well. A mercuric enol would be formed similar to the anti-addition of water and mercury in an alkene. Normally, this would require reduction with sodium borohydride, but the mercury can, in this case, help to facilitate the tautomerization and does not need to be reduced. The mercury salt used here doesn't really matter and can be used in catalytic amounts, since it's never actually reduced. This is a powerful reaction, but practically really only useful for a terminal alkyne, where one carbon is more substituted than the end carbon, and the product is always the 2-ketone. Or a symmetric alkyne, where both carbons of the alkyne could give the same ketone. In the absence of those two cases, you end up with a mixture of products. Oxygen can also function as an electrophile, but it takes a special circumstance to make oxygen positive. The main source for a positively charged oxygen is metachloroperoxybenzoic acid, abbreviated MCPBA. Technically, any peroxy acid could react, but the MCPBA is widely used because it's very effective. The product of these reactions is an epoxide. Peroxy acids can form a cyclic hydrogen-bonded complex with themselves, and they already have a weak oxygen-oxygen bond. This allows for the concerted, which means all at once, receipt of electrons on the oxygen from the double bond, and stabilization of the other carbon with the extra electrons. Because the reaction happens all at once, there are no charged intermediates. Alkenes are easy to make, and MCPBA is relatively mild and selective. We can also make epoxides through halohydrins, which we discussed before, but that involves strong bases and takes multiple steps from an alkene, where this one is all at once. Because the reaction is at once, the trans-stereochemistry of the double bond is preserved in the epoxide, and only two enantiomers are formed. This is much messier with halohydrin-based epoxide formations, and so generally MCPBA is used whenever possible. There is another reaction that allows us to add an OH to an alkene, but at the anti-Markovnikov or less substituted location. This is called hydroboration oxidation. Interestingly, this reaction not only gives us anti-Markovnikov regiospecificity, it is also a way to give a syn addition of an H and an OH, so we always end up with just one set of enantiomers. Before we go too far down the road with hydroboration, let me tell you about a lie we've told you. Boron doesn't actually exist as BH3, and hydrogen can have more than one thing bonded to it. BH3 actually exists as a dimer with two 3-center bonds that contain 2 electrons apiece. All this to say, BH3 really isn't stable. It really does want to have that octet. But in your heart, you always knew this was the case. You never truly believed that BH3 could just not have an octet and be fine with it. If we dissolve BH3 in a solvent, which for this reaction is tetrahydrofuran, THF, the diborane will split, but still complex with the solvent for stability, like a weird goo that you can only get off if you stick it to something else. We'd like that something else to be an alkene. An alkene can readily donate electrons to a boron, which is an electrophile, but boron is actually less electronegative than hydrogen, so boron is the positive part and the hydride is the negative part. They add simultaneously through a 4-membered ring transition state that requires that they add to the same side. Boron is not huge, but it is big enough that the hydrogen is always going to go to the more substituted side because of steric constraints. This becomes even more pronounced when the reaction proceeds because the boron continues to be electron deficient and will continue to add to alkenes. With each addition, it becomes bigger and bigger, amplifying the steric considerations. The trialkyl borane formed is, of course, not an alcohol, but we can convert that trialkyl borane to an alcohol through oxidations. Boron and oxygen form stable bonds. Treating a trialkyl borane with peroxide allows boron to fill its octet, but the oxygen-oxygen bond is unstable, and the carbon can readily shift from the boron to the oxygen and kick out hydroxide. This is repeated until all of the carbon-boron bonds are replaced by carbon-oxygen bonds. Hydroxide can then coordinate to boron, one at a time, and each of the alkoxides can dissociate, one at a time. The net result is a syn anti-Markovnikov addition of water. BH3 can react similarly with alkynes, but the alkyne product can react with additional BH3. It's actually kind of a problem. You end up with a huge mixture of products. Dicyanmylborane, an abbreviation for disec-isoamylborane, can be used instead because the large sec-isoamyl groups only allow for a single addition. Subsequent oxidation gives us a terminal enol. Keto-enol tautomerization of this molecule doesn't give a ketone, it gives the aldehyde instead because it's terminal. As is increasingly the case, we have a lot of reactions that need both memorization and understanding. All of our reactions in this chapter formed 3-membered ring products or small ring transition states that help drive the reaction, the regiochemistry, and the stereochemistry. Because no carbocation is produced, these reactions are much more controlled and do not rearrange. One ring product that we can form is cyclopropane, but that requires us to form a carbene first. These are incredibly reactive and can only be made in the reaction itself. We can also form rings with molecular bromine or chlorine, which will react to form cyclic intermediates. In the absence of another nucleophile, the halide anion will react with the intermediate to form a dihalide. In water, the water will act as the nucleophile instead and will form a halohydrin. Oxymercuration reduction allows for the Markovnikov addition of water, but it doesn't rearrange. Epoxides can be formed using peroxy acid, and usually we use MCPBA. Hydroboration oxidation allows for the anti-Markovnikov addition, so it's the opposite of the oxymercuration reduction. We can also use mercury catalysis of alkyne hydration, and that yields ketones. Or we can do hydroboration of alkynes, but it will only work with a bulky borane like dicyamylborane, which will give us an aldehyde. And as always, there are summary tables at the end of your chapter.